Okay, hello everyone. I hope you're all fine, and I hope that the new year is so far so good. So I welcome you back from your holidays, and we shall start with serious business again. So this year I want to start with a different topic, and that is relations, functions, and digraphs. With time, you'll get to know what each of these mean. But for the moment, we are going to start with relations. Functions and digraphs will come later. Okay. And under relations, we are basically going to look at, say, maybe what they mean in mathematics, how to find the product sets, which are also sometimes called the Cartesian products. Then what are binary relations, which are also called ordered pairs? How do you find the cardinality of these products or the relations that we are going to look at? What are some of the properties of Cartesian products? And under this, we shall look at things like the cardinality of the Cartesian product, how many subsets do they have, and so on. Okay, so when we talk about relations, I don't want you to think about something abstract. I just want you to think of, okay, so your university students, and probably you have big sisters or big brothers in the families where you come from, and I'm sure you all know about relationships. Okay, I'll use that example to explain. So if you say that two people are in a relationship, for example, we have Viola and Joseph being in a relationship. Remember, these are two people who have not grown up together. Viola comes from a different family. Joseph also comes from a different family. So that's what this paragraph here is trying to talk about, that you have two people, a husband and a wife, and they're all coming from different families, but now they are coming together to form a relationship. Okay, so just like that real life example, in mathematics we can also have relationships, which we shall simply call relations. And these relationships are on numbers or letters or different sets, but not on people, as in the example I've given you. And what do we use to see these relationships or to form these relationships? We shall make use of the arrow diagrams, and also we have the set builder notation. This is also commonly used to write relations. I hope you still remember what a set builder notation is. In case you don't remember, here is an example. You looked at it when you're looking at sets. So you have this R equals a B such that A, B belongs to A. So this is a way of writing elements of a set using the set builder notation. Okay. So you're saying that if R is a relation on a set A, so you've said that for us in mathematics we shall do relations on numbers, letters, and so on. And these numbers or letters definitely come from a set. So we shall be using the notation of sets very often. Okay, so we have a set A and we want to define a relation R. We've said that a relation consists of two items. Okay, but now in this case the relation is on just one set. In the example I gave you of Viola and Joseph, Viola comes from a different set, Joseph comes from a different set. But there are also situations where you define a relation on just one set. you ask me, okay, which example can you think about in real life? I'll look at an example of a family, and maybe you look at all the girls in the family. So all those girls are coming from some family A, and then you try to establish a relationship between the girls. For example, you can say if you have, say, 3 sisters, sister A, sister B, sister C, you can say sister A is younger than sister B. So you form that as the relationship. One is younger than the other. Okay? Yeah. So this then tells us that if you're putting elements of a set and you want to form a relation, that means you have to pick some element from a set and also pick another element from a set. Hence, that notation is now what we call the Cartesian product, and we write it as A times A. Yeah, but this times does not mean multiplication. So I don't want you to compute this and say that here you get A squared. This just tells us that we are picking an element from here, comma, then another element from here to form a pair. If it was A cross B, I think let me use the term cross instead of times. If you're using A cross B, it means the first element is from A, set A, while the second element from the pair is from set B. Okay, and I've said that this product here is what we call the Cartesian product. So we are going to see how to compute the Cartesian product given sets. Okay. Another very important thing which I want you to note is that if you have a relation, and so now you know that a relation consists of 2 elements, or a pair of 2 elements, right? So you have a relation xy, and you also have another relation yx. These two are not the same, because we've said that for you to have a relation, you get the elements from from 2 sets. So if you have a set A, suppose this x is from set A and this y is from set B. Yeah. So if you again say that this pair will be the same as yx, it would mean that x and y are from the same set, which is not true. Okay, so we cannot have commutativity when it comes to relations. These 2 pairs are always treated as different. So there's an example here which I gave to demonstrate more on this. They are saying that X represents Tom is a student at Nkozi, and Y represents Kampala city. The relationship you can formulate between these two, maybe you can say that Tom is a student at Nkozi and he stays in Kampala or lives in Kampala. Okay, so suppose that is the relation we have formed between the two. So if a person then interchanges these to begin with Y and then end with X, which relation can you form from there? You can find that in whichever way, we know Y represents Kampala, then X represents Tom is a student at Nkozi. So it becomes hard for you to think of a possible relationship between these two. And the same applies to, for example, this relation R, where the rule is that X has to be less than Y. So if X is less than Y, it means that you have pairs of two elements, but the first one is smaller than the second one. For example, here 5 is smaller than 30. So if this is the relation and then someone interchanges and begins with 30, 5, then this would not make any sense, because the relation says that X is smaller than Y. So this example is just to tell you that whenever you have pairs in a relation, then you cannot interchange them. Okay. So let's look at some examples here. We have a relation R from defined as this, meaning we are putting together elements from set A and elements from set B. So they have given us a set A consisting of these elements 0, 1, 2, and set B consisting of the elements A and B. So how do you find the Cartesian product of this? So to find the Cartesian product, as I said, it's a matter of pairing two elements. But you must make sure that what you're pairing is coming from different sets. So the easiest way would be to get each element in set A and pair it with each of the elements in B. Okay? So let's begin with 0. If you get 0 and pair it with A, then you shall have this pair. 0, pair it with B, then you shall have this pair. So we are done with 0. We move to the next one. 1. 1, you pair with A to get this 1A. 1 paired with B to get 1B. The same applies to 2. 2 paired with A, you get 2A. 2 paired with B, you get 2B. So these different pairs which you get are what will form the Cartesian product A cross B. And now let's look at a relation R given by this set. So realize that this R consists of just some pairs from the Cartesian product. That's why we are saying that R given by these pairs is a subset of the Cartesian product. I think now you know what a subset is. If a set X is a subset of Y, it means that all the elements in set X can be found in Y. And indeed, you can see that all these pairs here can be found in this Cartesian product. Okay. Then there is an example. Okay, example 2. I want you to ignore this. I don't like a lot of words. I'm a mathematician, so things which with too much wording don't go well with me. So just ignore that. Let's look at this next example. So given a relation R and the rule on R is less than or equal to, then they are saying that find R on the set 1, 2, 3 such that A is less than or equal to B. So they want us to find a relation on this set. This time they have given us only one set. So in this case, we have to get the Cartesian product A cross A. So I want you to compute the Cartesian product here. For each element in A, pair it with all the elements in A. So to make it easier, it's better to write set A as this, then write another set A below and list all the elements 1, 2, 3, then start pairing each element in the first A with all the elements. Yeah. So if you do that, then these are some of the pairs. For example, for 1, we shall have 1 paired with 1, 1 paired with 2, 1 paired with 3. Okay. Then you move to the next one. 2 paired with 1, 2 paired with 2, 2 paired with 3. I hope you have a pen and a pencil to try that out. Then you move to the last one. 3 paired with 1, 3 paired with 2, 3 paired with 3. So all those will be the elements in the Cartesian product A cross A. But from all those elements, they want you to find R. R has the condition that the first element is less or equal to the next one. So when you are computing the Cartesian product here, you saw cases where I had 2, 1, 3, 1, 3, 2. It means that those pairs do not qualify to be in R. So finally we say that the relation R has only pairs 1 1. You can see that 1 is equal to 1, so it satisfies because we have equality here. Then 1 is less than 2, so it satisfies this condition that A is less or equal to B. So either the elements in this case, in this particular example, are either equal or the first one is less than the small one. Where do we get this R? Compute the Cartesian product A cross A, and then look at all those pairs and then pick out the ones which satisfy this condition that either the first element and the second element are equal or the first element is smaller than the second one. So I hope you will try that out and see what you get. What you get actually should be this answer. Then there is another example. We have a set A given by this 1, 2, 3, and 4. Then find the relation described by this. So they want you to find the Cartesian product on this set, and then after pick out all those pairs which satisfy this condition. A divides B. What does A divides B mean? A divides B means that when you get B and divide it by A, you get remainder 0. Okay? So I want you to first compute the Cartesian product on this set, and then after, from all those pairs which you're going to get, choose out the ones which satisfy this condition. And we are saying that the answer is this. I don't want to spoon feed you. You're learning, so you have to do things yourselves. Yeah, I don't always like spoon feeding students. So I like it more when you discover things on your own. Yeah. So this is the answer which you should get, so you should try it out. And from this answer you can see that each of the two elements here, the first one represents A, the second one represents B. When you get B and divide by A, for all these pairs you get remainder 0. Let's see. 1 divided by 1, remainder is 0. 2 divided by 1, remainder is 0. 3 divided by 1, you get 3, remainder is 0. 4 by 1 satisfies. 2 by 2 satisfies. 4 divided by 2, it satisfies. 3 divided by 3 satisfies. 4 divided by 4 satisfies. So in this, you realize that we don't have pairs, for example, 3, 4. Because when you divide 4 by 3, you get a remainder. Okay? Yeah. So on this set, this R, which you have found to be this, is the relation which satisfies this condition that the first element divides the second one. Okay? So there are more examples here. A marketing research firm classifies a person according to the following two criteria. So they are giving us two sets. The first set depends on the gender. So you have elements M and F. M represents male and F represents female. While the second set consists of the levels of education. And they are being represented by these letters: E for elementary, H for high school, C for college, G for graduate. So now we have these two sets, which we are calling G to be the set for gender, and then L to be the set for the levels of education with these elements. And they want you to compute the Cartesian product. As I said, the rule is get each element in the first set and pair it with each of the elements here. So you find elements like ME, MH, MC, MG. Then you go to the next one, F, FE, FH, FC, FG. So that will be the Cartesian product. So there's that example. You can also look at it example 5. Then there is also example 6. You have these two sets, A and B, and they want you to compute the Cartesian product A cross B, B cross B, A cross A. I want you to try that out and see what you get. Okay. Okay. Then what is this? The relation is less than. Let R be the relation is less than on the set, and so on. Then R 1 1 1 2 2 1. I think this was supposed to be R is the relation is less than or equal to. Okay, yeah, so you should correct add less than or equal to. So you can see that all the pairs in this R satisfy this condition that A is less than or equal to B. Okay. So let's move to the next part, and that is representing a Cartesian product in matrix and diagram form. So this is also easy. Actually, is the easiest way in which you can be able to compute the Cartesian product, because that idea of saying that get each element in the first set and pair it with all the elements in the second probably may be confusing to some of you. But which other way can we use to find the Cartesian product? So that leads us to what we call the matrix form. So what happens under the matrix form? So we have these two sets. A, please take note, has elements x, y, z. B has elements 1, 2, 3. So to use the matrix form, you write all the elements of A as a column. Then you write all the elements of B in row form. What do I mean? Here is what I mean. So you write all elements of A, X, Y, Z in column form, and all elements of B in row form, and then we start pairing them. You see the first one with the first one here. So you have X1 to give us this, X2 to give us this, X3 to give us this. Then you move the next one, Y1 to give us this, Y2 to give us this, Y3 to give us this, and so on up to the last element. So briefly, this is the matrix form. So the reason why it is called a matrix is because the elements are listed like using rows or using columns. So you can try out this method for even the previous examples that we saw. Okay, so there's another example here. We have elements A as 1, 2, 3, 4, and elements of B as W and X. So you write elements of A as a column and elements of B in row form. Okay, and then you start pairing these together. So I think this, to me, is the easiest approach, because with this approach, it's very hard for you to miss out on some of the pairs. Okay. So please try to play around with that and see which answers you get, or see whether what you get agrees with what is in the notes. Okay, so there's another example here. Consider the following relations on Z. We have R1 as a relation consisting of elements AB such that A is less than or equal to B. R2 has AB such that A is greater than B. R3 has AB such that A equals to B okay, or A equals negative B. R4 has elements AB such that they are equal. R5 has elements AB such that A is equal to B plus 1, and so on. Okay? So then they are saying which of these relations contains each of the following pairs. So you have a pair 1 1, 1 2, 2 1, 1 negative 1, 2 2. So they want you to look at each of these pairs and see whether they satisfy R1. Do they satisfy R2? Do they satisfy R3, R4, R5, and so on? For example, let's look at 1 1 and R1. R1 says you have a pair AB such that A is less than or equal to B. So either A has to be less than B or they must be equal. So I think this first pair satisfies. Let's move to the next one. Does it satisfy R2? R2 says you have a pair AB where A is greater than B. So for this pair, our A is 1, our B is 1. They are equal, so they don't satisfy R2. Okay, we go to R3. AB such that A equals B or A equals negative B. We don't have anything negative here, so it doesn't satisfy R3. When you come to R4, R4 we have A equals to B, so it satisfies R4. Okay, so far we've seen that it satisfies R1, it satisfies R4. How about R5? R5 is saying that you have a B such that A is equal to B plus 1. Yeah? So this one means that the value of A is bigger than the value of B by 1. Examples which you can have here are, for example, 3, 2, okay, 4, 3, and so on. The first two, the difference between the first and the second is 1, meaning the first one is bigger and the second one is smaller by a 1 difference. Okay, so this does not satisfy R5. How about R6? For R6 we have AB such that when you add A and B, the sum which you get is less than or equal to 3. So let's add 1 plus 2. 1 plus 2 is 2. Is 2 less than or equal to 3? Yes. So the first pair satisfies R6. So how many relations does the first pair satisfy? It satisfies R1, it satisfies R4, it satisfies R6. So I want you to do the same for each of these other pairs and see where they are satisfied in each of these relations. Okay, so that's what this example was trying to look at. Okay, so in this case, let me see, R3, I think this must have been a mistake. Let's see, what is R3? Oh, R3 we have a B such that A is either equal to B or is equal, yeah. So, yeah, this was a mistake. For R3, we have this. There are two conditions. It can either be this one, A equals to B, or A equals negative B. Okay, yeah. So you can see that the pair 1 1 is being satisfied by R1, R3, R4, and R6. So that's why we have these stars here. R1, R3, R4, and R6. I want to try for these other pairs 1, 2, 2, 1, negative 1, and so on. So where there is a star, that is where the relation is being satisfied. Okay, yeah, so that's also another exercise for you. Then we also have the previous approach of finding the Cartesian product was the matrix method, but you also have the diagrammatic representation, and this can also be referred to as the arrow diagram. Okay, so we use arrows to map elements from each of the sets to the other. Yeah, so let me first pause this video here. I don't want to make a very long one. Okay, so in the next video I'll start from the diagrammatic representation. Thank you all for listening, and please make sure you try out all those exercises I've given you. Okay, bye.